The machinery that built the modern digital economy has officially hit a dead end. For the past decade, a single technology, known as Standard Extreme Ultraviolet Lithography, or EUV, quietly powered every major leap in global hardware innovation. But that engine has stalled. Engineers have finally reached the absolute physical limits of what this machine can do. If we cannot push past it, the trillion-dollar semiconductor industry grinds to a halt. To print the microscopic transistors inside your phone, standard EUV relies on a highly specific wavelength of light, measuring exactly 13.5 nanometers. But there is a strict boundary in optics, known as the Rayleigh criterion. It dictates that light cannot be squeezed indefinitely. When that 13.5 nanometer beam reaches 8 nanometers, the light ceases to behave predictably. Instead of etching a clean, precise pattern onto a silicon wafer, the light diffracts. It spreads out into a useless blur, making it impossible to resolve the intricate circuitry needed for a working chip. The tech industry, however, doesn't care about the physical limits of optics. To build the next generation of artificial intelligence, chip makers demand ever smaller transistors. Engineers have arrived at the hard limit of standard lithography. To continue shrinking transistors, they can no longer rely on traditional optics. They have to move toward a much more violent, brute force manipulation of light. The solution to that physical wall was engineered in the Netherlands at ASML, taking the form of a brute force system called High-NA EUV. Inside this machine, a high-powered carbon dioxide laser fires into an empty chamber. It intercepts falling droplets of microscopic liquid tin and vaporizes them into pure cyan plasma. This is not a continuous beam. This microscopic collision happens 50,000 times every single second. The sheer violence of this reaction generates extreme heat. The plasma reaches 220,000 degrees Celsius. If that reaction happened in open air, it would instantly destroy the facility. It must be contained entirely within a perfect, manufactured vacuum. Generating power 40 times hotter than the surface of the sun is an active war against nature. It is the only remaining way to squeeze light small enough to continue manufacturing modern chips. Creating that violent energy is only the first step. Capturing it requires a delicate capture mechanism built by Zeiss, specifically anamorphic mirrors that bend the light at an extreme numerical aperture of 0.55. To ensure these mirrors work, the measurement system used simply to verify them weighs over 150 tons and sits inside a custom-built 10-meter vacuum chamber. The precision is difficult to comprehend. If one of these mirrors were scaled up to the size of Germany, the single highest bump on its surface would measure 100 micrometers, about the width of a human hair. Polishing metal to an atomic level takes time. A single set of these mirrors requires well over a year to manufacture. The continuation of Moore's law, the steady historical shrinking of computer chips, now depends entirely on a bespoke process that completely defies mass production. Once the atomic mirrors and the extreme light source are finally married together, you get the EXE5000 platform, a machine that dominates the sterile environment of a fabrication plant. It is the size of a double-decker bus, weighing 165 tons, roughly the mass of a blue whale. Buying a single unit will cost a chip foundry roughly $400 million. Intel has taken the first-mover advantage, aggressively deploying this mammoth technology at their Oregon facility, aiming to produce their new 14A node chips by 2026. But TSMC, the current leader in global semiconductor manufacturing, has deliberately paused. They calculate that the exorbitant price tag outweighs the immediate technical benefits. The future of sub-2 nanometer hardware now bifurcates. One path relies on immediate, high-cost adoption, while the other waits for the economics to stabilize, a divergence that will define the hardware foundation of the next decade. As these machines become the sole path forward for high-end logic, they've shifted from industrial tools to geopolitical leverage. The U.S. has moved to strictly limit who can buy them, effectively creating a technological blockade around the most advanced manufacturing nodes. And yet, inside the closed doors of Veldhoven, engineers are already mapping out the successor to High-NA, and even more extreme architecture known as Hyper-NA. Pushing past the limits of light didn't end the struggle for smaller chips. It simply proved that each subsequent breakthrough will demand increasingly extreme engineering and billions of dollars in new capital just to stay in the race.